Ever wondered why the blueberry is considered the ultimate diva of the horticultural world? The answer isn't in the fruit, it's hidden deep in the rhizosphere. With a fragile root system that lacks hairs and a biological intolerance for the very soils most crops love, these plants demand absolute environmental mastery. Today, we are unlocking the technical secrets of blueberry edaphics. We'll explore how to engineer the perfect environment, from the mysteries of pH control to the high-tech substrates that make commercial success possible in the most challenging climates. Are you ready to see what it really takes to grow this blue gold beneath the surface? Let's dive in.
Welcome back to The Explainer. Today, we're pulling back the curtain on a hidden, highly technical world that, honestly, most of us never even think about when we're just browsing the produce aisle. We're zeroing in on the fascinating and surprisingly clinical science of commercial blueberry cultivation. Because you see, growing these little blue fruits at a massive scale, it's not just your traditional farming. It is an absolutely incredible feat of biological engineering and edaphic precision. Okay, let's dive into this. Notice this amazing handful of fruit right here. It's a beautiful, extremely high-value crop that looks super robust and abundant, right? But beneath the surface, hiding down in the dirt, this plant has a profound biological vulnerability. It is literally an evolutionary diva. Its root system is fragile, highly inefficient, and it demands an environment that's practically impossible to find naturally in the world's major commercial growing regions. To actually get this fruit, growers have to fight nature every single day. So to understand exactly how they pull this off, here's our roadmap for today. We'll be hitting 1. The biological paradox, 2. The acidic mandate, 3. Hostile native soils, 4. Engineering the rhizosphere, and wrapping up with 5. Precision chemistry. Let's jump right into Section 1, the biological paradox, and take a look at the bizarre anatomy of the blueberry root. Think about your standard agricultural crop. Usually, you've got a robust root system. Picture a big taproot plunging deep down into the earth, totally covered in microscopic root hairs that are aggressively out there foraging for water and nutrients. Well, the blueberry, it's the exact opposite. It has this highly superficial, super fibrous root mat that is completely devoid of root hairs. Because it's missing those hairs, it's naturally incredibly inefficient at absorbing what it needs to survive. And worse, because it forms this dense, shallow mat, it is ridiculously sensitive to waterlogging. If the soil doesn't drain perfectly, this hairless root system will quite literally suffocate and drown. Which brings us perfectly to Section 2, the acidic mandate, focusing on the plant's uncompromising pH rules. So in strict botanical terms, blueberries are what we call calcifuge and strictly acidophilic. That basically means they actively despise basic calcium-heavy soils and absolutely require a highly acidic environment, specifically a pH level sitting right between 4.0 and 5.5. And I really want to be clear about this. For a blueberry plant, an acidic pH isn't just a slight preference or some handy tip for better yields. It is a strict biological mandate. Break this rule and the plant essentially starves to death, no matter how much fertilizer you throw at it. Now, what's really interesting about this slide is the chain reaction that triggers the second we cross that 5.5 pH threshold. We call this the chlorosis cascade. The very instant the substrate pH ticks above 5.5, a physical chemical blockade drops down. Iron, which is a totally critical micronutrient, physically locks into these insoluble compounds right within the soil matrix. So the plant's inefficient, hairless roots completely fail to absorb it, leading directly to rapid, severe stunting of the plant's growth. And here is what that failure actually looks like out in the real world. This super vivid interveinal yellowing you're seeing on the leaves, that's the classic clinical presentation of pH-induced iron chlorosis. Notice how the veins stay green, but the rest of the leaf turns this really sickly yellow? That's because it literally cannot photosynthesize properly without that locked-up iron. When a grower walks the field and sees this, it's an immediate red flag that the strict acidic mandate has been broken. Okay, so we know what the plant demands, but how does that stack up against real commercial environments? Let's hit Section 3, hostile native soils, and look at the arid reality. Take a look at this typical arid agricultural landscape getting prepped for planting. A huge portion of the world's commercial blueberries are actually grown in Mediterranean climates, places like Morocco or Spain, because honestly, the weather and the sunlight above ground are absolutely fantastic for fruit production. But down beneath the surface, there is a massive problem. The native soils in these regions are naturally basic, highly calcareous, super heavy in clay, and often just packed with salts.
It is quite literally the exact opposite of the acidic, well-draining environment the blueberry evolved to live in.
This data perfectly highlights what we call the edaphic gap. Look at this. The plant demands a pH under 5.5, organic matter above 6%, and way over 30% air-filled porosity. But the harsh reality of arid farmland gives you high pH, almost zero organic matter, and heavy compacted clay. Plus, remember how we said blueberries are highly sensitive to salinity? Well, these arid lands are loaded with salts and carbonates. Trying to dump chemicals on this native earth to force it into a highly aerated, acidic, low-salt oasis, it's incredibly inefficient. It's basically a losing battle. So, if the native soil is that completely hostile, how on earth do we grow millions of pounds of blueberries there? The answer is in Section 4, Engineering the Rhizosphere, by bypassing the soil entirely.
Instead of fighting the dirt, modern commercial growers just replace it. They engineer entirely artificial soilless substrates. What you're seeing here are workers mixing up a highly precise blend of peat, coconut coir, and perlite. The peat and the coir are giving us that essential 6% organic matter and holding the water. Meanwhile, the perlite, that white coarse volcanic glass, guarantees the mix maintains a strict 30% air-filled porosity. That ensures those fragile, hairless roots we talked about earlier never ever suffocate.
And this brilliantly illustrates how the strategy actually deploys in the field. You've got these endless rows of customized substrate put directly into pots, sitting literally right on top of the hostile native soil. By moving the plants into these isolated containers, the growers entirely bypass the basic clay-heavy earth. They have effectively constructed millions of individual, perfect, totally customized root zones, or rhizospheres, tailored exactly to the blueberry's weird biology. But, just throwing some engineered dirt into a pot isn't quite the whole story. To really support this system, a massive biological and chemical regimen gets deployed. For instance, nitrogen has to be provided exclusively in the ammonium form, because the standard nitrate form can actually injure this specific plant. The substrate is slowly, continuously acidified over time using elemental sulfur. They use mulches like sawdust or pine needles to lock in moisture. And honestly, the most fascinating part? They introduce symbiotic ericoid mycorrhizae. These are specialized fungi that physically fuse with the roots, effectively acting as surrogate root hairs to help the plant pull in nutrients. It's brilliant.
Now, building this perfect environment is one thing. Maintaining it out in the middle of a hot, arid climate brings us to Section 5, Precision Chemistry and Constant Management.
So the crucial point is that this requires intense, clinical, day-to-day precision. Every single drop of irrigation water is meticulously monitored. Because arid water is usually just full of carbonates, growers have to continuously dose the water with sulfuric or phosphoric acid to ensure it hits the pot at a completely perfect 5.0 pH. Concurrently, they are constantly testing the electrical conductivity, or EC, of the water draining out the bottom of the pots, making sure it stays well below 2.0 millisiemens per centimeter. If that EC spikes, it means lethal salts are building up, and those fragile roots will quickly burn and die. It is literally a constant razor's edge balancing act. So, look at what we've done here. We've essentially built an agricultural intensive care unit. We've catered to every single biological paradox, we've isolated the roots, and we've dialed in the precise chemistry every single day just to keep this delicate plant alive and happy. But surviving isn't the goal here, right? The goal is commercial yield. So what happens when we take this highly sensitive, perfectly engineered system and we push it to its absolute biological limits to pump out thousands of pounds of massive, energy-dense berries? Well, that is exactly what we're going to explore in Part 2.
Welcome back. So, if you joined us for the first part of this explainer, we spent a lot of time geeking out over the blueberry plant's incredible, but honestly, super demanding botanical makeup. Well, today, we're taking all that fragility we talked about and crashing it right into the harsh, dirty realities of the earth beneath our feet. We're getting into the strict edaphic, or soil-related requirements of this plant, and looking at the massive, game-changing shift happening right now in how we actually grow them. Just to quickly set the stage, I want you to cast your mind back to that critical point from our last session. Remember the blueberry's incredibly fragile, completely hairless root architecture? Since it's missing those vital root hairs that most plants use to explore the soil, it's stuck with this extremely shallow, sensitive fibrous root system. It needs massive amounts of aeration. And waterlogging? Huge enemy. Literally, one bad rainstorm and heavy soil, and those roots can just suffocate.
Okay, let's dive right into this. Because of that delicate root structure, the plant is basically locked into a strict biological mandate.
Out in its native, peaty, boggy habitat, this plant survives by teaming up with these specialized fungi called ericoid mycorrhiza. And this partnership, it's strict. It dictates an absolute, non-negotiable need for an environment packed with organic matter and incredibly low salinity. You can't just shove a blueberry bush into any random dirt. It demands a highly engineered, totally specialized root zone. So here's our roadmap for today. First, the acidic mandate. Second, diagnosing starvation. Third, the calcareous trap. Fourth, the soilless solution. And finally, precision chemistry. Section 1. The acidic mandate and those strict pH requirements. All right, let's start with the absolute non-negotiable chemistry required for a blueberry plant to even survive, let alone thrive. Look, if there's literally just one number you take away from this entire explainer, make it this: 4.5 to 5.5. That is the ultimate pH sweet spot for the root zone. Native peats can actually drop down to 4.0, and if you're brave enough to cultivate in mineral soils, you really need to hold the line strictly between 5.0 and 5.5. The margin for error is razor thin here. Dip below 5.0 in mineral soils, and you're looking at aluminum and manganese toxicity. But if you accidentally creep up past 6.0, yeah, the plant's entire biological engine just shuts down. In the botany world, the blueberry is known as a calcifuge. Basically, it's strictly acidophilic. It essentially runs away from chalk and calcium. Its physiology is hardwired in a way that it literally cannot process or absorb essential nutrients if the soil is neutral or basic. It's crazy. The food could be sitting right there, completely surrounding the roots, but the plant's uptake mechanisms are just locked tight. Section 2. Diagnosing starvation and what high pH actually looks like. So what actually happens when a grower breaks this strict acidic rule? Well, check out the distinct intervenal yellowing on these younger leaves. That is iron chlorosis. It's the absolute classic textbook visual symptom of a plant going through high pH starvation. Like we just said, the iron is probably right there in the dirt, but because the pH is too alkaline, the iron physically precipitates out. It's totally blocked from absorption. And it's not just iron. The uptake of manganese, zinc, phosphorus, copper, they all just plummet at the same time. The plant is literally starving to death while sitting at a fully stocked, all-you-can-eat buffet. Section 3. The calcareous trap and dealing with hostile soils. Historically, farmers tried to fight this by just brute forcing their native dirt, which, honestly, leads right into a brick wall. And this brilliantly illustrates the core nightmare for growers in places like the Mediterranean, Morocco, or huge parts of the US. These native soils usually have a basic pH, a lot of times sitting above 7.0, and they're just loaded with active calcium carbonate, meaning they are fundamentally hostile to blueberries. The sheer buffering capacity of the lime in these deep clay soils makes holding a stable acidic root zone practically impossible over the long haul.
If you actually want to plant in this stuff, you have to gear up for a grueling biological war. It's not some quick chemical fix. Step 1, sourcing massive amounts of elemental sulfur. Step 2 means aggressively ripping it into the ground 15 to 30 centimeters deep with heavy machinery. And step 3, you wait. You literally have to wait up to an entire year for specialized soil bacteria to slowly, painstakingly oxidize that elemental sulfur into sulfuric acid before you can safely put a single bush into the ground.
And honestly, the economics of this old-school fix are absolutely punishing. To drop the pH by just a couple of points, a sandy soil might need around 740 kilograms of sulfur per hectare. Not great, but manageable. But if you're dealing with loam or clay soils that have a high cation exchange capacity, oh man, you are looking at upwards of 3,400 kilograms per hectare. That heavy clay acts like massive chemical resistance. It constantly releases basic ions, fighting you every step of the way, and forces that pH right back to toxic levels within just a few years. It's an exhausting, unending treadmill.
Which brings us to Section 4, the soilless solution, and how we completely bypass the crisis. So how exactly do modern, large-scale commercial operations deal with this impossible dirt problem? Well, they don't. They completely pivot. And this is the massive paradigm shift that is completely reshaping commercial blueberry farming today. Growers are just walking away from the native soil entirely. Instead, they're filling these massive containers with engineered substrate. By isolating the plant in pots, they instantly bypass the local soil quality and perfectly satisfy that biological mandate of the roots on day one.
Inside those pots is a very specific, carefully dialed-in recipe. First, you've got peat, acting as that naturally acidic organic foundation, kind of mimicking the plant's native boggy home. Then you mix in coconut coir. That gives you structural stability and the perfect amount of moisture retention without breaking down too fast. Finally, perlite. Those little white rocks you see in potting mix, those maximize the macro porosity to guarantee the extreme aeration those fragile roots absolutely need. You mix it all together, and you get this perfectly drained sanctuary sitting at over 6.0% organic matter.
Section 5. Precision chemistry and the daily exact science of it all.
Now, what's really interesting here is that building the perfect physical substrate is honestly only half the battle. Once you shift into containers, farming turns into a daily, highly exact science. Check out the EC meter over on the left. We are managing electrical conductivity here, keeping it exceptionally low to protect those sensitive roots from chemical burn, all while delicately balancing nutrients like ammonium. And on the right, a beautiful pH reading of 4.83. Growers hit that by using precise daily fertigation. They inject exact calculated microdoses of sulfuric or phosphoric acid straight through the drip lines, locking that root zone right into that perfect 4.8 to 5.5 sweet spot.
So, when we bring it all together, the choice for a modern grower becomes pretty obvious. Sure, open ground soil has way lower initial costs, but it takes a year to prep, you're constantly fighting highly unstable pH, and there's that looming, ever-present risk of root decline and iron chlorosis. On the flip side, container substrates demand a massive initial capital expenditure, buying the pots, mixing the media, the whole 9 yards. But the setup is immediate, the pH is incredibly stable, and you get this precise, long-term control over your yield. That is, of course, assuming you don't mess up your daily fertigation math.
And here is the ultimate reward of all that precision agronomy. A perfectly unhindered, massive harvest, pulled straight out of an environment where the native dirt would have killed the plant in months. Seeing this really leaves us with a pretty profound question for the future of agriculture, doesn't it? When we can completely engineer the perfect root zone on demand and basically bypass the earth entirely, are we still farming the land, or are we simply farming the plant? Something to think about until our next explainer.
Welcome back, everyone. Okay, let's jump right into the action. We're moving directly into part 03 of our blueberry cultivation explainer. We're totally skipping the basics today because we need to plunge right into advanced root zone engineering. If you caught parts 1 and 2, you already know this crop is incredibly demanding. But today, we're going to unpack exactly why it's so demanding from the ground up and how growers actually engineer solutions for it in the real world. So, here's our quick roadmap for today. Number 1, the blueberry root paradox. Number 2, Pillar 1, chemical acidity. Number 3, Pillar 2, physical porosity. Number 4, Pillar 3, the biological engine. And finally, Number 5, field execution. All right, Section 1, the blueberry root paradox. Now, this right here is a sheer agronomic contradiction. Think about it. We've got this massive, highly profitable global crop, but it relies on an incredibly fragile foundation. The blueberry has a fine, fibrous, and very shallow root system. And here's the absolute kicker. It literally lacks root hairs. That severely limits its ability to forage for nutrients. Combine that limited foraging with an extreme waterlogging sensitivity and a zero-tolerance policy for heavy mineral clays, and, well, you start to see why native soils almost never meet these exact demands. Moving on to Section 2, Pillar 1, chemical acidity. So the absolutely crucial point here is that blueberries are calciphage. That means they despise alkaline soils. They are strictly acidophilic. Notice the pH readings we're looking at here, strictly maintaining that mandatory range of 4.0 to 5.5. And honestly, this isn't just a gentle suggestion. It's an absolute requirement to ensure nutrients actually dissolve. Also notice the continuous monitoring for EC, or electrical conductivity. Because of those fragile roots we just talked about, blueberries have incredibly low salinity tolerance. You have to constantly monitor for low EC to prevent immediate root burn. And if you mess that up, well, here's a classic real-world case of iron chlorosis. See that striking interveinal yellowing on the young leaves, where the veins stay stubbornly green? Interestingly, it's not actually a lack of iron in the soil. It's a direct symptom of edaphic mismanagement. The moment that pH creeps above 5.5, iron becomes chemically locked up. The plant literally starves, even though the food is sitting right there. Section 3, Pillar 2, physical porosity. Because of those fine fibrous roots, heavy mineral clays are a literal death sentence. They cause fatal waterlogging. These roots demand highly oxygenated pathways. The ideal textures are sandy loams or loamy sands, with absolutely zero tolerance for compaction. The modern agronomic standard we are aggressively shooting for here is a mandatory minimum of 30% air-filled porosity. The roots literally have to breathe to survive and expand. Section 4, Pillar 3, the biological engine. Okay, before you even think about planting in native soils, you have to engineer the biology. We're talking massive amendments of acidified plant compost dumped directly into the planting holes. This single step brilliantly tackles both moisture retention and that mandatory soil porosity we just covered. It's really all about building a highly hospitable home before the plant even arrives on the farm. And let's break down that biological engine a bit more. We need organic matter significantly above standard agricultural baselines. We're talking greater than 6.0%. Why so high? To create a rich, fungi-forward ecosystem. Blueberries rely incredibly heavily on a symbiotic relationship with ericoid mycorrhizae to extract nitrogen, specifically in the form of ammonium or NH4+, as well as phosphorus. Plus, this deep organic layer acts as a vital thermal buffer for that shallow root zone, and it drastically increases water holding capacity without sacrificing our required porosity. Section 5. Field execution. Soil versus soilless. Let's see how this actually works. This edaphic engineering matrix is basically the core decision board for any serious grower. Now, native Mediterranean soils, for instance, often have terrible drainage and make pH control nearly impossible. But hey, the capital expense is low. Then you have Pathway A, raised beds. This improves drainage via gravity and allows moderate pH control with a medium expense. But then there's Pathway B, soilless substrates. This gives perfect engineered porosity and absolute pH control, albeit at a very, very high capital expense. The level of financial investment scales exactly with the grower's need for absolute environmental control. Let's look closely at Execution A, soil modification. You can see heavy machinery constructing elevated ridges or raised beds. This brilliantly illustrates how growers literally harness simple physics. By elevating the root zone, gravity naturally pulls moisture away from the crown, artificially preventing the waterlogging that so quickly destroys those fibrous roots in heavier mineral soils. But what if your native soil is just way too heavy or way too alkaline? Well, you bypass the earth entirely. Execution B is the total transition to soilless substrates. The roots are completely isolated from native soil in these pots. This allows growers to use incredibly precise fertigation. They deliver exact pH solutions, sometimes utilizing carefully measured sulfuric or phosphoric acid and perfectly calibrated EC directly to a highly engineered root zone. It's a total game changer. So you're probably wondering, what exactly is inside those pots? Let's deconstruct the anatomy of a stable substrate. It's a very precise recipe. Ingredient 1 is crushed pine bark. This is the structural anchor. It aggressively resists decomposition and settling over the plant's 5+ year lifespan. Ingredient 2 is a tailored blend of peat and coconut coir, providing the ultimate moisture holding capacity and that vital baseline acidity. And finally, ingredient 3 is perlite, which physically guarantees we hit that non-negotiable greater than 30% air-filled porosity. Just check out the manual execution of this precise recipe happening right out in the field. These real-world photos show how it's done. You can distinctly see the different textures coming together, right? The dark peat and coir, the chunky pine bark, and the stark white perlite. It's an act of literal soil construction, creating the absolute perfect calcifuge environment from scratch. And take a second to consider the intense labor and raw material input required here. Every single pot has to be properly filled and leveled, with the irrigation lines perfectly placed, before a single solitary blueberry bush is ever planted. The upfront engineering and capital expense are truly staggering when you see it all laid out. But listen, the engineering doesn't just stop on planting day. Let's talk long-term maintenance. Sustaining this incredibly fragile ecosystem requires dedicated, continuous mulching. A mandatory 5 to 8 centimeter layer of peat, sawdust, or pine needles is applied. This aggressively suppresses weed competition and prevents lethal soil crusting over those delicate, shallow roots. Plus, using materials like pine needles or even occasionally applying elemental sulfur offers a gentle, continuous acidification of the soil over the years to naturally maintain that strict 4.0 to 5.5 pH requirement. Seriously, just let the sheer scale of this operation sink in for a moment. Row upon row, thousands upon thousands of isolated, perfectly engineered environments. This is what absolute, uncompromising environmental control looks like on a modern commercial scale. They've taken a mathematically complex agronomic challenge and totally solved it by simply bypassing the native limitations. Welcome back. We are on to part 04 of our Blueberry Cultivation Masterclass Explainer. Now, we've already covered a ton of ground in the previous sections, so today we're skipping the fluff. We are diving straight underground to look at the complex, frankly kind of paradoxical, root zone of the blueberry plant. It's all about the extreme precision required to keep this highly sensitive crop not just alive, but actually thriving. Okay, let's dive right into this because the blueberry root system is biologically bizarre. It's strictly confined to just the top 20 to 30 centimeters of the soil. We're talking about an incredibly shallow fibrous root system. And here's the real kicker. These roots completely lack microscopic root hairs, none at all. That means they are inherently terrible at extracting water and nutrients on their own. So to even survive, let alone produce commercial yields, the plant relies heavily on a critical symbiosis with ericoid mycorrhiza. Think of this specialized fungus as a set of biological root extensions scavenging for nutrients in harsh, highly organic environments. It's literally a lifesaver. To manage this intense vulnerability and the incredibly shallow root system, agronomists rely on a strict zero-tolerance framework. We can break this down into three vital pillars: the physical pillar, the hydrological pillar, and the chemical pillar. Let's see how they overlap. Starting things off with Section 1, the physical pillar, or preventing root asphyxia. For blueberries, aeration isn't just about optimal growth, it's literally a matter of life and death. Because these roots are so superficial, they're incredibly sensitive to waterlogging. Agronomists call this deadly condition hydromorphy, and we have to avoid it at all costs. Since natural soils almost always fail to provide these exact conditions, growers are increasingly turning to heavily engineered soilless substrates. These require a minimum organic matter content of over 6.0%. The foundation here is what we call the substrate trinity matrix. First up, peat. That guarantees your baseline acidity and crucial moisture retention. Second, coconut coir. This adds stable structural integrity, so the whole thing doesn't just collapse over time. And third, coarse materials like perlite or pine bark. This last ingredient is absolutely non-negotiable because it guarantees an air-filled porosity, or AFP, of greater than 30%. Now, what's really interesting about this out in the field is that 30% air-filled porosity we just talked about is immediately obvious. You can clearly see how the coarse perlite and bark leave these vital physical gaps within the dark organic base. Those visible pockets of air ensure that oxygen constantly reaches the rhizosphere, which is just that immediate zone right around the roots. Without that continuous airflow, the roots simply suffocate. Which brings us right into Section 2, the hydrological pillar. This is all about continuous hydration without saturation. This is where the grower basically has to become an engineer. Think about it. You have a plant that desperately needs high oxygen, so high drainage to prevent asphyxia, but it also has an incredibly shallow, inefficient root system that needs constant moisture. It's a severe hydrological paradox. 40. That is up to 40 cubic meters of water per hectare per day. To put that massive number into perspective, it's like dumping a heavy-duty commercial dump truck full of water onto your field every single afternoon at peak summer demand. But because of that super shallow root structure we discussed earlier, heavy, infrequent watering is completely useless. The water just drains right past the 30-centimeter root zone, and the plant is left totally parched just a few hours later. To handle this crazy balancing act, growers employ a strict flushing strategy. They use frequent, short-duration, localized drip irrigation pulses. We're talking multiple tiny pulses a day just to maintain exact moisture equilibrium. But there is a huge catch here. Blueberry roots are exceptionally sensitive to salt toxicity. If you stick an EC meter into the soil, which measures electrical conductivity to detect salt buildup, that number has to stay remarkably low. Because of this, every single day, growers must deliberately over-irrigate to create a runoff volume of 15 to 25%. This deliberate runoff mechanically flushes all those accumulated toxic salts right out of the root zone, keeping that EC strictly locked between 0.75 and 0.9. But here's the thing. All that physical and hydrological effort, completely useless if the chemistry is wrong. So, moving on to Section 3, the chemical pillar, or the strict acidity gatekeeper. A really crucial term you need to understand here is calcifuge. By definition, a calcifuge is a plant that absolutely will not tolerate alkaline soil. It is uncompromisingly acidophilic. For blueberries to survive and actually take up nutrients, they demand a highly acidic, tightly locked pH window of exactly 4.0 to 5.5. Ideally, growers are targeting a perfect 5.0. Now, what happens if you step outside that 4.0 to 5.5 pH window? Or what if physical drainage fails and creates prolonged saturation? Well, the biological consequences are immediate and severe. Going above that pH threshold causes the roots to essentially lock out nutrients, which instantly triggers severe iron chlorosis. You'll see this as sickly, distinctively yellowing leaves. On top of that, poor aeration and waterlogging are the ultimate triggers for soil-borne pathogens like Phytophthora cinnamoni. And that leads straight to root rot, stem wilting, and eventually total crop failure. So the crucial point to take away is that this highly acidic microenvironment doesn't just happen on its own, and it certainly doesn't maintain itself. It requires aggressive, active chemical interventions. First, growers use pre-planting soil amendments packed with elemental sulfur to crash the initial pH. Second, there's a continuous acidification of the irrigation water itself, usually by pumping sulfuric or phosphoric acid right through the drip lines. And third, there is a strict preference for ammonium-based fertilizers. Why? Because as the plant absorbs the ammonium ion, it naturally releases acid, which perfectly reinforces that acidic microenvironment right around the roots. Let's bring this all together. To actually succeed here, a grower must master these overlapping systems all at the same time. Physically, you absolutely need over 30% air-filled porosity and over 6.0% organic matter. Hydrologically, you are balancing a massive peak demand of 40 cubic meters of daily water per hectare, coupled with a 15 to 25% mechanical flush. And chemically, you are relentlessly locking that pH down between 4.0 and 5.5, while keeping the electrical conductivity strictly between 0.75 and 0.9. It's the mastery of this specific, fragile matrix that transforms the blueberry root from a biological liability into a massive engine for high-yield commercial production. Before we wrap up this explainer, I want to leave you with a thought. As you've seen, this entire process is incredibly engineered, highly demanding, and intensely water-reliant. So as global temperatures continue to rise and fresh water becomes increasingly scarce in agricultural regions, how is climate change going to test the extreme, delicate precision of these systems? Next time you eat a handful of blueberries, ask yourself, can we realistically sustain this level of strict hydrological and chemical control into the future? It is a huge puzzle, and it's something every single agronomist is worrying about right now. Thanks so much for joining me for this breakdown. Welcome back to The Explainer. So today we're building directly on the plant architecture concepts we covered in previous parts. But now we're diving into the ground right beneath the plant. Or, well, actually, the engineered substitute for it. We're getting into the edaphic mastery of the blueberry. Let's get started. Here's our roadmap for today. We'll be looking at bypassing the soil barrier, engineering the perfect substrate, the aeration mandate, precision daily monitoring, and finally, how all of this leads to accelerated commercial yields. All right, Section 1, bypassing the soil barrier. You know, native calcareous soils are incredibly tough. They inherently possess a really high pH and active calcium carbonates, which literally starve acidophilic plants like blueberries by blocking nutrient uptake. You can actually see the severe iron chlorosis kicking in, that yellowing distress in the leaves. If planted directly in the ground in these regions, root death and total crop failure are pretty much inevitable. So what's the workaround? Well, we don't even try to fight the native soil. We just completely bypass it. To achieve any sort of commercial viability, growers are using a 100% soilless container cultivation strategy. By dropping these plants into massive 40 to 50-liter pots, we physically isolate that fragile, fibrous root system. It's a total game changer because it gives us absolute control over the entire environment. Moving on to Section 2, engineering the perfect substrate. Okay, so if we're totally replacing the native soil, we have to engineer the absolute perfect medium from scratch. It starts with creating a foundation that is both highly acidic and incredibly porous. We're talking about a very specific blend of materials designed to perfectly mimic the blueberry's ideal natural habitat, but, fully optimized for massive commercial scaling. And here is that exact substrate formula. We use 40 to 50% acid peat to provide that essential ultra-low native acidity. We're targeting a pH of 3.5 to 4.5 here, along with superior water-holding capacity. Then we balance that peat with 20 to 30% washed coconut coir. Now that coir absolutely must be thoroughly pre-flushed to get rid of any excess sodium and chloride. And finally, we mix in 20 to 30% coarse perlite or silica sand, specifically using particles larger than 5 millimeters. Which brings us to Section 3, the aeration mandate. This is absolutely crucial. Unlike your standard nursery crops that might only need 10 to 20%, blueberries require an air-filled porosity, or AFP, that is strictly greater than 30%. You really have to think of their fibrous root systems like fragile little lungs. They are exceptionally sensitive, and if you leave them in waterlogged conditions, they will literally drown. And that's exactly why we mandate those coarse perlite particles larger than 5 millimeters in the mix. When you combine that chunky substrate with abundant drainage holes and actually elevate the pots on physical legs, you guarantee rapid drainage. It's the only way to truly secure that aeration mandate and protect the roots from asphyxia. All right, Section 4, Precision Daily Monitoring. Now, because artificial media has an exceptionally low buffering capacity, which essentially means its chemical state can swing wildly depending on the irrigation water, we are forced to perform daily clinical interventions. Growers have to constantly monitor both the electrical conductivity, the EC, and the pH of the water draining from these pots. It's an everyday process to constantly refine that chemical environment. Let's talk about the absolute red line for the nutrient availability zone. Automated acid dosing in the fertigation system absolutely must maintain a constant root zone pH, strictly between 4.5 and 5.5. Using acidified water for every single irrigation cycle is quite literally the only way to unlock those vital micronutrients and completely avoid that devastating iron chlorosis we saw earlier. But pH is really only half the battle here. We also have to meticulously manage the salts coming from the fertilizer. As water naturally evaporates and the plant absorbs what it needs, those fertilizer salts inherently accumulate inside that tightly restricted pot volume. Left unchecked, this causes sudden, highly dangerous salinity spikes, so systematic leaching becomes an absolute daily necessity. To prevent that toxic salt buildup from happening, growers are mandated to maintain a leachate runoff volume of 15 to 25% during every single irrigation cycle. Basically, you have to push enough water through the pot to continuously flush the entire system out. Testing this drain solution every single day ensures that the root environment remains continuously flushed and perfectly chemically stable. The golden rule? You have to keep the electrical conductivity of that drain water strictly below 2.0 millisiemens per centimeter. Seriously, if it creeps above that 2.0 mark, you're risking severe root burn and major crop damage. And finally, Section 5, Accelerated Commercial Yields. So what does this all mean? What's the ultimate payoff for this incredibly intense, precision-engineered protocol? Well, by achieving total pH mastery and perfect root zone aeration, we guarantee this incredibly uniform plant establishment. This level of absolute environmental control allows the crops to entirely bypass those hostile native soils. And the result? They hit mature commercial yields incredibly early. We're talking about realizing the plant's maximum genetic potential often by year 1. It's truly amazing. This explainer leaves us with a genuinely fascinating thought to consider. If we can out-engineer nature this effectively for a crop as famously demanding as the blueberry, utilizing precision substrate mastery to turn a fundamentally hostile environment into a highly profitable one, what other so-called impossible crops can we cultivate next? Think about that for a bit. Thanks for joining, and we'll see you in the next explainer.
Welcome to The Debate. Usually when we think of agriculture, planting a seed is, well, an act of trust in nature. But today, we are looking at a massive dilemma for commercial blueberry growers.
Right, a very expensive dilemma.
Exactly. Like, if the earth beneath your feet is fundamentally toxic to your crop, do you spend millions trying to fix the soil? Or, do you just abandon the earth entirely and grow in pots? I represent the perspective that we can heavily modify the native open ground.
And I strongly disagree with that approach.
Right. And joining me to present that opposing view is agronomy expert Dr. Fahd Amlao, who represents the Soilless substrate approach. To clearly establish his position, let's play a direct audio testimony from his recent field lecture.
In the field, don't farm hostile soil. Engineer the rhizosphere instead. Use soilless containers for total isolation. This fragile root system requires 30% air-filled porosity to breathe, so target a pH of 5.0 and maintain 15 to 25% leachate daily to prevent catastrophic salt burn.
So welcome to the studio, Dr. Amlao. That clip really lays it out. But my position is that native soils can be modified to meet the strict biological mandate of the blueberry plant. We do this through, edaphic engineering.
Right, but I stand entirely by what you just heard in that testimony. Calcareous soils, meaning soils heavily loaded with calcium carbonate, are fundamentally incompatible with this plant.
You think it is totally impossible?
Trying to negotiate with that kind of earth is, well, it is a losing battle. It will inevitably ruin your crops.
Well, I want to challenge that idea of it being an inevitable failure regarding chemical strict acidity. How do you justify completely abandoning soil when deep incorporation of elemental sulfur can successfully oxidize and stabilize a 4.5 to 5.5 pH over a year?
I come at it from a different way. You have to look at how Mediterranean clay soils actually operate. They act like a massive chemical sponge loaded with calcium.
Okay, a sponge.
Right. When you add sulfur, you do lower the pH, but it is temporary. Because of the soil's high cation exchange capacity, that clay sponge slowly and continuously squeezes out basic ions.
Ah, so within 3 to 4 years, your pH creeps right back up to toxic levels. And when that pH crosses 5.5, that is where we see the iron absorption blocked, correct?
Exactly. Because blueberries evolved in highly acidic bogs, they lack the specific root enzymes that other plants use to pry iron away from alkaline soil. When the pH rises, the iron chemically locks up.
So the plant essentially starves in a well-stocked pantry.
Yes, leading straight to intravenous iron chlorosis. It is devastating.
That is a compelling way to visualize it. But we manage that slow release of basic ions with ongoing surface acidification. However, even if we win that chemical battle, we still face a physical one.
A massive physical battle, yes.
Right. If the soil is too dense, a perfect pH will not matter because the plant will drown. Which brings up your requirement for porosity.
Yes. Given the blueberry's fragile, hairless root system concentrated in the top 30 centimeters, how can open-ground mineral soils guarantee the non-negotiable greater than 30% air-filled porosity?
Without risking fatal waterlogging.
Exactly. Without that massive amount of oxygen, they sit in dense mud and suffocate from root rot.
I see why you think that, but let me give you a different perspective. Open ground cultivation is not just planting on flat, dense earth.
Okay, what do you do instead?
We utilize elevated ridges, or billons, which harness gravity to actively pull moisture downward and away from the crown.
But is gravity really enough to guarantee 30% airspace?
It is when paired with a mandatory 5 to 8 centimeter layer of pine needle mulch. That mulch prevents lethal soil crusting over those shallow roots.
Oh, the pine needles.
Yeah, and as those needles break down, they actually provide a gentle, continuous acidification of the soil.
Gravity drainage helps, certainly. But moving to total isolation in a container guarantees perfect physical architecture from day one. You aren't hoping the soil breathes. You know it does.
Perhaps. But doesn't a 40 to 50 liter container system create a, terrifyingly fragile microenvironment?
Fragile? Not at all.
Well, if you isolate it, the slightest mistake in your fertigation causes catastrophic salt burn. A trapped root system has nowhere to escape.
I'm sorry, but I just don't buy that. Let me tell you why. Bypassing the earth with a mix of acid peat, washed coconut coir, and perlite transforms root zone management into precise daily science.
But you are still relying on a very small margin of error.
We aren't guessing, though. By monitoring electrical conductivity continuously at 0.75 to 0.9 dcm, we essentially measure the exact salt concentration.
Wait, so you eliminate the risk of salt burn just by watching the meters?
By watching them and forcing 15 to 25% of the water to drain out the bottom as daily leachate. Those toxic elemental salts are constantly washed away.
So they never accumulate. That is a remarkable level of precise control.
Yes, washed away before they can ever burn the roots.
I agree it is precise, but it abandons the long-term biological resilience of properly amended open ground. A living soil ecosystem buffers mistakes over decades.
While that may be true for perfect native soils, in these harsh environments, isolated soilless substrates provide the absolute chemical and physical control necessary to unlock commercial yields.
Ultimately, there is a clear point of convergence here. We both agree that blueberries demand an uncompromisingly acidic and highly aerated environment to survive.
Exactly.
The strict biological mandate of the plant does not change. Only our engineering methods do.
And so we return to that initial act of planting. We leave it to the listeners to consider whether they choose to negotiate with nature's complex chemistry or engineer their way entirely around it.